Alright, now we are going to solve this example 11 from the textbook. Well, let's read the question. I have the figure on the board so that not to waste the time. Well, here's the question. The electric field components in this figure are Ex, which is alpha x raised to 1 by 2, or 800x raised to 1 by 2 because alpha is 800, Ey equal to 0, Ez equal to 0. What this means is that the electric field is only in the x direction, it's not in the y nor in the z direction, right? So, all the electric field is in the x direction. Right? It's not uniform, as you can see. It's not uniform because it depends on x, right? Okay, so let's continue. Calculate A, the flux through the cube. So for this cube, which is a closed surface, right? Cube is a closed surface. We have to find out what is the electric flux through that cube, okay? And B, the charge within the cube. Okay, well, let's start with A, and it's given that assume that the length of the side of the cube or edge of the cube is A, which is given to be 0.1 meter, right? So let's start with part A of this problem. So we have to find out the electric flux through the cube. Now, first of all, I want you to imagine the electric field lines. When all the electric field lines are going to be towards the right hand side, that is towards the x axis. So if you think of this flat surface, the upper one, I am sure you do realize that the electric field is in the right hand side, but the normal vector of this upper surface is in that direction, pointing towards the y axis. So the angle between the electric field and that normal vector or the area vector is going to be 90 degrees. And if this angle is 90 degrees, cos 90 degrees is 0. So the electric flux for this upper surface is 0, right? Okay, see, the plan here again is to divide this complicated shape into simple parts, into flat surfaces, right? Okay, so a cube has 6 flat surfaces. We find it for this one, it's 0, right? Now let's go to the second flat surface, the one over here. Again, same problem, the electric field is in the right hand direction, it's on the x axis, but this normal vector is pointing downwards, right? Okay, so because of that, the flux for this one is also 0 because the angle is 90. So as far as the flux through the cube is concerned, flux through the cube is concerned, well, we have flux for this upper surface 0. We have the flux for the lower surface as 0. We have the flux for the surface in front as 0 again, because here again the electric field and the area vector to the front surface is going to make an angle 90 degree. Let me give you an example by using this duster. Let's see. Here is the cube, assume that, and this is its front surface. If I'll put the area vector of this particular surface, it's going to be pointing towards you like this, right? Normal to the surface and going outwards, right? Don't forget the important points. But the electric field is in that direction. So you can see what happens is that the electric field line, the area vector is towards you, but the electric field lines are going towards the right hand side. So because of that, what we have is there is a 90 degree angle between these two, and that's why the flux for the front surface is 0, right? Just like it was for these two. And similarly, the flux for the surface behind is also 0 because its area vector is just in opposite direction. So once again, the angle is still 90. So finally, if I want to find the flux through the cube, I just have to do it for 2 surfaces, the one on the left and the one on the right. Okay, so let's talk about the one on the left. So for the one on the left, the electric field obviously over here in the right hand direction, but this is a flat surface, right? This is a flat surface. Then should we use the formula E vector dot S vector, or should we use the formula integration of E vector dot ds vector? Well, I know it's confusing. The best way to get out of it is think about all these points on this left surface. At all these points on the left surface, the x coordinate for any of these is x equal to a, which is 0.1. So do you realize that at every point on this surface, the value of Ex is going to be 800 into a raised to 1 by 2, right? At all these points. Okay, right now we are talking about this surface number 5. So for all the points on this surface, the value of Ex is the same because that x coordinate is same. So it is that as far as this surface is concerned, we can say that the field is uniform and we can use that formula. Correct? Because the surface is flat and we can consider the field to be uniform as far as that surface is what we are talking about, right? So finally, there is no need to use this one for number 5. So what I am going to write is for flux through the cube, I can write that phi is equal to flux through surface number 5, add to that the flux through surface number 6. So we get the total flux. For 1, 2, 3 and 4, the flux is 0. So this is equal to, okay, flux through surface number 5. E vector dot S vector, that's what you could do. Or you could do Es cos theta. I'm going to do it by Es cos theta. So Es cos theta, right? This is just a placeholder. I don't mean to, write that really. It's okay. Even if you don't write it on your paper, we just have to put the values. E's value for this 5, this surface number 5, is going to be 800 into a raised to 1 by 2. Okay. Now, surface area of that surface, it's a square, right? Because the whole thing is a cube, so it's a square. So its surface area is going to be a square because edge length is a. And now cos theta. Well, look at this, E vector going this way, the normal vector going that way, outwards. The angle between these two is 180 degrees, and that is why I should be writing cos 180 degrees, right? I hope phi is clear, right? Such a coincidence. And now we go to number 6. Again, we are going to use same tactics because this is once again a flat surface. Not only that, for all points on this, the x coordinate is going to be 2a, right? A till here, a more, so 2a, correct? So now if I want to write down what is the flux through that surface, I can once again use Es cos theta. So E is going to be 800. Now come back to this. If you want to find E of x, that is in x direction, it's 800 and then x coordinate raised to half. So now the x coordinate is 2a. It's not a anymore, it is 2a. So 2a raised to 1 by 2, okay, into the area, so that is a square, right? And now we come to cos theta. So what's the direction of electric field? Again, it's towards the right hand side at all points. So what's the angle between electric field vector and the area vector or the normal vector, which is going outwards? I'm sure you see that the angle is 0, right? So ultimately, this is the expression of electric flux. See, it's very simple to do it on your own, right? It's just that we have to take care of these minute details. It's not that tough really. So what we get? Well, 800 a raised to 1 by 2 a square cos 180 degrees minus 1 plus. Now over there, 800, I'm going to separate this one out. So into 2 raised to 1 by 2 or root 2 into a raised to 1 by 2 into a square cos 0 is 1, right? So we can take 800 common, we can take a raised to 5 by 2 common. I'm getting 5 by 2 by addition of the powers, right? What's remaining in the bracket? Well, this is gone, minus 1, and over here 2 raised to half, that is root 2 remains. And now I can put the value of a, right? So that is going to be 800 into a's value is 0.1, right, raised to 5 by 2. So 10 raised to minus 1 raised to 5 by 2 into root 2 minus 1, right? Okay. So well, this is the answer we get. It's looking very complicated, I know. So at the most I could do 8 into 10 raised to 2 into 10 raised to minus 5 by 2 into root 2 minus 1. So that turns out to be 8 into 10 raised to minus 1 by 2 into root 2 minus 1. This is your final answer of the flux in Newton meter square per coulomb. If you want, you can take a square root of 10 using your calculators. I don't have a problem with that, right? So this is how we found the flux for this cube, right, placed inside such an electric field, right? The key idea of this question is that we have a closed surface, all right, but we already know about the electric field. So we find the flux for that whole cube by splitting it into some easy parts, right? So those easy parts are 6 faces, 6 sides of the cube, all right? So that's it, right, for the answer of the part A, right? Now there's part B, right, in which we have to find out how much charge should be there inside this cube, right? So let's start with that, part B. Right. So we have to find the charge inside this cube. Now to do that, I'm just going to write the symbol and you will understand what we have to find. We have to find the charge enclosed in the cube. So the easiest way to do that is use the Gauss law, which says that for this closed surface, means for this cube, I can say that the flux is equal to sigma q enclosed divided by epsilon 0, right? So we put the value that we have got here, right? We put this value, right? And we can find the charge enclosed is equal to phi into epsilon 0. Phi is this, so 8 upon root 10 into root 2 minus 1 into epsilon 0, that is 8.85 into 10 raised to minus 12, right? And finally, the unit is going to be coulomb. I leave the calculations for you, all right?